Good day. I am Jumbo. You can call me JB. So I'll be taking you on finite element method today. What is finite element before I continue? When you talk about finite elements, like you are sectioning a body into pieces. Now, when it comes to finite element method, after you section this body into small piece, then you want to solve it and find the structural property of these elements. It could be strength, it could be anything, it could be the stress acting on the object. So let me give you the definition of finite elements method. Finite elements method is a numerical technique that is used, first of all, take note of this, a numerical technique that is used to find solution or to find an appropriate solution to a BVP problem. What is BVP? Value boundary problem using differential equation. So we have got the definition of finite elements method. That is what? Technique is a numerical technique that is used to find an approximate solution to a boundary value problem using differential equation. So consider these objects. So this is an object, and let's call this points UI, and let's call this points UJ. So this object, considering it, a force is being applied at this end. It's just like a cantilever. A force is being applied at this end. So when the force is applied, there's going to be an extension. And you can remember from Hooke's law, he said that the force acting on an object is directly proportional to the what? To the extension. That is what Hooke's law states. So since the force acting on an object is directly proportional to the extension, it simply means that we can find the proportionality here, which is what? F equals to KE. So take note, K is called the string stiffness. So K is called the string stiffness, and the unit for K is Newton per meter. Please take note of all these dimensions because this can even reduce your mark while solving. So you must always take note of dimension. So we say that F is directly proportional to the what? Extension. And since Hooke's law has given us like a general principle, I don't want to go like I don't want to dive into proving this formula for Hooke's law, but I'll just give a general notation so that we can go into calculation. So for solving this kind of body, I said this is like going to be the first element. This is going to be another element, right? So for this body, sectioning it into sections, we have Fi and Fj. So Fi and Fj simply means force acting on these points, and Fj simply means force acting on this point. Is equals to, remember, F equals to Ke. So is equals to let me call it Kp now because it is a general K. And this Kp is standing for the stiffness for K1 because it's going to be like a string stiffness here, and there's going to be another string stiffness here. So Kp, then Ui, then Uj. So please first take note of this expression, that is Fi, Fj. So they call this one the force vector, and this is the displacement vector. Take note, this is force vector and this is displacement vector, and Kp is the stiffness acting in this entire body. Now how do we now find Kp? That is where the question comes in. So before we go into finding how to get Kp, I'll first tell us the algorithm we follow in solving finite elements problems. When you want to solve a finite element question or question on finite element analysis, I'll be using analysis as the context because when we talk about analysis, we are trying to analyze. It's still the same thing as almost the same thing as finite elements method. So they are quite similar to one another. So in mechanical engineering today, if you ask, talking about finite element, you always talk about finite element analysis because we are making analysis. But the approach you use is called finite element method. So to solving any question under FEN, the first thing you're going to do is that you have to define the problem. What is the problem you have to solve? So let me give you like a problem on the board. We want to consider a cantilever, and this is the cantilever here. This is the cantilever. Now this cantilever, a force is being applied. Perhaps let me say the force is applied at this point, which you are still going to consider later. The force can be applied here. The force can be applied here, anywhere. You get that? So the force can be applied there. It can even be applied at this point. But there are different approach to this. So let me start from here. You say define the problem. We know the problem we want to solve. The problem we're going to solve is called, let me call this point F. So that is the force that's being applied there. So we know the problem we want to solve now. That is, this is the problem, a cantilever, that a force is applied at this point. Let me call the point O. So the first thing, define the problem, and this is the problem. We have defined it. Now the second problem is what's called discretization. Now what is the meaning of discretization? It simply means you have to section the elements that are being given, I mean the entire body, into several elements. That is, divide into a finite element. That is where the terminology comes from. Say finite element. You are going to divide that body into what? Finite element. So that's why it is countable. It is not something that we cannot count. So look at this body now. You know that I can divide this body into two, right? So at this point, I can call this one point. So in finite element, there's something called node. We have node. So the node are the point of reference. Take note. Node that was the point of reference. So the first node they have here is this point. Another node is here. Another node is here. So we have how many nodes here? We're having 3 nodes. Now, how many elements do we have? Then your element is gotten by counting the number of elements in the node. So look at this point now. How many nodes do we have? 1, 2, 3. Just subtract one from it, you get your number of elements. So if you subtract from 1 from 3, what do you have? 2. That simply means we have 2 elements. So this is an element from the point to this point. From this point to this point is an element, and from this point to this point is what? Is another element. So what you have just done now is called discretization. That is, you are sectioning the body into finite elements. Excuse me. So the next one is what? Define the element stiffness. It means that for each component, you have to define is what? Its stiffness. Then how do we do this? You can remember that Hooke's law states what? It says F equals to what? Ke. And you can still remember that from this Hooke's law, we are being told that Young modulus is equals to what? Is equals to stress over strain. Now we know that Young modulus is the same as E, and stress is the same as what? Sigma, and our strain is the same thing as let me represent strain with let me say E. Let me say E. So sigma is the same thing as E dot epsilon. E dot epsilon. So since my sigma is what? E dot epsilon, I still remember that this epsilon, which is the strain, is the same thing as the change in displacement, which is what? Your extension. So let me call the change in displacement to be, let me call it under this point that we are using U, then U over L. So that simply means what? Our stress is equal to what? AU over L. Now remember that this is stress. That this stress is simple as what? Force over area equals to what? AU over L. Now, if you make our first order formula, F equals to what? F equals to AE U over L. Now, if this is ascertained that it is true, if I split this, I'll be having AE over L dot U. Now, remember from Hooke's law, he said what? F equals to KE. But remember, I said that in this concept, we are using U for our E. F equals to what? KU. Therefore, if we equate F equals to AE over L dot U to this, we'll be having our K to be equals to AE over L. So that is what it simply means. That is, this is our string stiffness. So define the element string stiffness. So for this one now, if you want to find the element string stiffness, let me clean this point. So you can always pause the video and just go through what is there before you proceed to the next step. We said K is equals to AE over L. So that is for element 1. For element 1, that means K1 is equals to A1 E1 over L1. For element 2, which is K2, equals to what? A2 E2, L2. Now it doesn't matter. The element can be of the same material. So if they have the same material, it simply means what? Your Young modulus what will be the same. So it doesn't matter, but ensure that you have different parameter for different elements when it comes to the string stiffness, because the area can be the same and the area can always be different. The what's it called? The length can be the same, the length can be different. So it depends on the question you are being given. So that is why you'll be able to identify the parameters in the question. So after you define the string stiffness, the next thing is that you are going to assemble the global stiffness matrix. Then after you assemble the global stiffness matrix, you will solve it. Then you what? Do post-processing and validation. So I want to quickly do something, consider this body, then I'll follow the whole process. After following the whole process, then we'll get the what? KP. You know I told you something about KP the other time. So KP is the global string stiffness, but we also have string stiffness for individual elements. So this is the body. I said the first thing you're going to do is you have known the problem. So we need to discretize, right? Discretization. So the first thing about discretization is that you must determine your node. So I said this will be the first node. Let me call this node 1. This will be the second node, node 2. And this will be the third node, node 3. And I told you for you to get the number of elements, just subtract 1 for what? For the number of nodes. So 3 minus 1 will give us 2 elements. So that means at this point I can section it to be here and here. So from this point to this point, and from this point to this point, so this is element 1 and this is element 2. So that simply means that for element 1, it simply means we have F1. Now consider this node 1 to node 2. So for node 1 to 2, node 1 to 2, it means there's going to be a force here and there's going to be a force here. So let's call the force here to be F1 and the force here to be F2. Follow me. The force here to be what? F1 and the force here to be F2. Now if the force here is F1 and the force here is F2, the string stiffness acting on this element itself, let's call it K1. So it simply means that K1, let me give you the general matrix for string stiffness. So K1 minus K1 minus K1, K1. So this is the string stiffness on element 1. There's a way we get this. I don't want to prove it because of time. So just stating that this list is just following your matrix. Plus, minus, minus, plus. That is just the principle. So this is K1, K1 for everything. Then follow the plus minus. For example, if we are looking for cofactor, we follow plus minus. So just follow that plus minus for this one as well. It works. So K1 minus K1 minus K1, K1. Then the displacement vector from 1 to 2 is going to be U1 because there's going to be displacement here and there's going to be another displacement here, U2. I want us to visualize these things together. If you look at this object, if the force is applied here and it's being stretched, right, there's going to be a displacement at this point because this point will be here. And when you apply a force here, it will shift a little bit. It's just like a bridge. So if there's going to be extension, like too much of stress on the bridge, it's going to extend. So that's what this one is going to extend. But is this one going to extend? No. It's not going to extend. That simply means that U1 here will be what? 0. We still get to calculation aspect. I'm just trying to show us the algorithm. So we have F1, F2, K1 minus K1 minus K1, K1. So this K is the stiffness of this element 1. And U1 are the displacement at this nodal points. So the nodal here, which is the node here, the first acting here is F1, and the node here, the first acting here is what? F2. So let's go to another one for node 2 to 3, because we'll be considering node by node, from one node to another, from one node to another. That is how we are going to be solving it. For node 2 to 3, the first that will be acting here will be F2, then F3, which is the first acting at this node, equals to, now, the stiffness for this element, let's call it K2. So K2 minus K2, I want to say the next one for me. Yeah, if you say minus K2, you are right. And if you say this place is K2, then you are right as well. So This will be U2, and if you say this place is U3, then you are right. All right. So this is the stiffness, the components of element 2, and everything you have here is the component of element 1. Now, we said after you have done discretization, you have to assemble. After you define the string stiffness, you have to assemble the whole elements. So you have to assemble it together. Then how do you assemble it together? We do what they call interpolation. We interpolate the body and we merge it together. So follow me. See how we're going to do that. So this element 1, we have element, they have F2 here. We also have F2 here. So F2 will merge F2, and every other element will be repeated. So for the assembling, so when you assemble it, you have F1, F2, F3. Now for this one, look at it. How many? We're having like 2 by 2 here. We also have 2 by 2 here, right? So if you have 2 by 2, the matrix that is going to give you is going to be a 3 by 3 matrices. Why? How do I know this? Go back to your node. How many nodes do you have? 1, 2, 3. It still means that's what? The number of matrices you're going to get at the end of the day is what? 3 by 3 matrices. Now, let me show you how you're going to form the global string stiffness. This is K1. Now, this K1, you're going to repeat everything here. You repeat it here. We have K1 minus K1 minus K1, K1. Now, this is where the merging will come in. Look at this. You are going to put this element, you will put it here, and it will intersect. So, at this point, you know this is our leading diagonal for this matrix, K1. So, the leading diagonal, at this point here, you are going to merge this K2. So, when you merge it, everything will still follow the same flow. So, we have K1 plus K2. Then, the next thing here is what? Minus K2 minus K2, K2. Then, what will be left? Nothing is there. What do we put? We'll just put 0, because that place will just be empty. You can see how many, what is the dimension of this matrix? It is a what? 3 by 3 matrices. And the same thing, the principle applied for the forces also apply to what? To the vector. To the vector of the displacements. So the displacement vector now be U1, U2, then U3. So what we have just done now is what? It's called assembling. We assemble the elements together. This is the example that we'll be considering. Let me call this one first example, example 1. So we said consider a bar as shown below. This is the bar. You can see it. That the bar, if it observes something, the bar is terminated there. So this one simply means like a stiff body. For example, if you look at this marker now, and this marker is attached to this body. So this body is called the reference point, that is where it is attached to. That simply means it is not moving. It is static. That place is stiff. So it is stiff here and also stiff here. So that means this object is not going to pass this boundary. You get that? So an axial force or axial load. So axial load simply means force. An axial load of 200 kilonewton, that is applied at point O. Where's point O? This point O. The force is applied here. Take the area and Young modulus of element of 1. So this is 1, element 1, and this is element 2. So take the area and Young modulus of element 1 as 240 millimeter squared and 7 times 10 power 9 Newton meter squared. Sometimes you can see this one as 70 gigapascal. Yeah, you know, Newton meter squared. 1 Newton meter squared is the same as 1 pascal. So you can see this one as 70 gigapascal. Then, respectively, why the respective properties of element 2 are 600 millimeter squared and 200 times 10 power 9 Newton per meter squared. Or you see this one also as 200 gigapascal. Pascal. So respectively. So the question is calculate the following. Hey, the nodal displacement as point O. That is the displacement you're going to have at this point O. Then another one, which is question B, stress in each element or in each material. So stress that is induced here in this body and the stress that also induced in this body, that will determine it. And we have to determine the reaction force. That is the force of reaction that will be here, the force of reaction that will be here, and the force of reaction that will be here. Now, I want you to take note of something, that when we are doing trusses, like if you can remember your solid mechanics, we have been taught like force can be in form of tension or compression. So this point, we don't know, maybe it is tension, we don't know, maybe this also is tension, we know this also is what, tension, but we have been told that the direction of this force is like this. It simply means what? It is what? Tension. So we don't know the force that will be acting here, we don't know the force that will be acting here, but by calculation we're going to determine that, and I'll tell you how to know maybe this force is tension or this force is what? Compression. Now, from the question, I was able to bring out this following data. That is the axial load we have been given at point O, which is F, is what? 200 kilonewton. And if we convert this back to Newton, that is kilo is equal to 10 power 3. So converting it back to a standard form, we have 2 times 10 power 5 Newton. So the area is 2,400 millimeters squared for element 1. So this is the area for element 1. Then for the Young modulus for element 1, we have been given to be what? 70 times 10 power 9 Newton per meter squared. So converting this one back to millimeter, that is Newton per millimeter squared. It's just like, let me show you how I got this. So this is 70 times 10 power 9 Newton meter squared. So if you convert this, how many millimeter give us 1 meter? It will be 1,000 give us. So we have Newton per 1,000 millimeter, everything squared. So if you square this, we have it 10 power 3 times 2. So 10 power 3 times 2 give us 10 power 6. So we are dividing this one by 10 power 6, which is what? 70 times 10 power 9 minus 6, which gives us 10 power 3. Then taking this also back to the standard form, we have 7 times 10 power 4 Newton per millimeter squared. I don't know if you get that, but just do this computation, you'll be able to get this. You can use your calculator to get it. Just divide this by 1,000 squared, because 1,000 millimeter is 1 meter. So if you square it and divide this one by the square of that 1,000, you're getting 7 times 10 power 4 Newton per meter squared. Why am I taking this back to millimeter squared? Because I have my area to be in millimeter squared. So the length we have been given for the object is, for element 1, is 300 millimeter. Then for element 2, we have been given this parameter that our area is 600 millimeter squared. The Young modulus is equals to, which is E2 equals to 200 times 10 power 9 Newton per meter squared. The same principle we applied here, also apply it here, which will be giving what? We'll be getting 2 times 10 power 5 Newton per millimeter squared. Then the next one is, we are going to have the length, which is given in the parameter as well, to be 400 millimeter. So if you go back to diagram, we have this, because now we have to do the discretization. We have this. So at this point O, the force is applied here. And don't forget that this also is sectioned. So we have a block here, we have another block here. So the force here is F. Now, let's section it. That is, we're going to discretize it. There's going to be a point here, which is a node 1. Another node there, which is what? 2. Another node there, which is what? 3. We have now what? Section it. We have discretized the body. So the next thing we're going to do is what? Now form the matrices. The vector matrix, the string stiffness matrix, and also the displacement matrix. Follow me. Now look at this. This is the body, right? So these are our first node, these are second node, these are our third node. And this is the element itself. We can remember from Hooke's law that's what? F equals to KU, where our K is what? AE over L. Please take note of this formula. If you forget anything, you should not forget this formula. And I trust God that you're not going to forget anything, right? So F equals to KU, then K is what? AE over L. A is the area, E is the young modulus, and L is the length. So from here, we are going to form the matrix. So consider for node 1 to 2. What do we have? We said let the force that be formed here be what? F1. The force that be formed here be F2. But remember that this force has a name. So we are still coming back to that. And this force that will be formed there should be what? F3. So for F1, from 1 to 2, we are having F1, F2. Then for this, which is the string constant, we have K1 minus K1, then minus K1, K1, then the displacement is U1, then U2. I know that this is not new to you anymore. That is, the force that is acting here is F1, and the one acting is F2. Then the displacement that will be here is U1, the displacement that will be here is what? U2. So that's the first parameter. Then we can actually get our K1. You know, I can still write this one to be, I can get it to be F1, F2. Then I can get this also to be K1, open bracket, 1 minus 1, minus 1, 1. Then I'll have U1, U2, U1, U2. So I can actually determine my K1. So what is my K1? My K1 for element 1 is K1 equals to A1 E1 over L1. So I know that my K1, which was given, my K1 is 2400 times my E1 was also given, which is 7 times 10 raised to the power 4 over the extension, which is 300 millimeter, which was given as well. So K1 equals to, so you can use a calculator to determine this. So when you use a calculator to determine that, then the answer will be 5.6 times 10 raised to the power 5. Please tell me the unit. The unit will be what? Newton per millimeter. Don't forget this. You must always put the units. So 5.6 times 10 raised to the power 5 Newton per millimeter. So we know from here that this is what? K1. Then we can now proceed for node 2. Node 2 to 3, we are having the same thing, F2, F3 equals to, then this one, let's represent with K2. The string stiffness in element 2 should be K2, then minus K2, then what? K2, then the string, the displacement vector will be U2, then to U3. So the same thing, I can also find what? I can also bring out my K2, which should be giving me F2, F3, then K2. This also will come to 1 minus 1 minus 1, 1. Then we have what? U2, U3. Now, we have this. So, what can I do? I can find my K2. Then my K2 be what? K2 equals to, this is 600. Sorry, let me give you the formula. K2 equals to A2, E2 over L2. Then K2 equals to 600 times 200 times 10 raised to the power. Now, I think I've converted this back to 2 times 10 raised over the length, which is 400. So 600 times 2 times 10 raised to the power 5 over 400. Then when you solve this using your calculator, K2 equals to 3 times 10 raised to the power 5 Newton per millimeter. Newton per millimeter. You can see we have gotten our K1, we are getting our K2. Now, the next thing we do is what? We assemble the components. So we assemble this node and assemble it with this node 2 to 3. Assemble the global stiffness matrix. So when you assemble it, you have F1, F2, F3. Then, now remember that we have K1 and K2. So, I can still have what? My K1. You can remember from that previous notation I gave you. K1 minus K1, 0, minus K1, 0. You can see that. K1 minus K1, 0. K1 minus K1, 0. Then you populate this place. How do you populate it? This place will be minus K1 plus K2. Then this will be minus K2, minus K2, K2. Then we have U1, U2, U3. U1, U2, U3. Now remember that I have gotten my K1 already. I have gotten my K1 to be equals to 5.6 times 10 to the power 9 Newton millimeter per millimeter rather. Then my K2 to be equals to 3 times, this is 5.6 times 10 to the power 5 Newton per millimeter. This one is 3 times 10 to the power 5 Newton per millimeter. Now, how do we get the force? Let me show you how we get the force. I'll draw the diagram again so that I'll be able to see it by using the diagram. So if you look at this, there's a force going in this area. Now, at this point, which is our F1, this is our 2, this is our 3. At this point, is there any force applied here? No. So that's something that the force here. Now, the difference between force acting and reacting force. The force of reaction is that when you pull this, the reaction that will be here is called the force of reaction. But the force acting here, is there any force acting here? No. So there's no force acting here. So we say that F1 at this point is what? 0. Now, is there any force acting here? Yes. What is the force? F equals to what? F. Now, if you look at this point, obstruction. So since there's obstruction here, it simply means that there's no force acting at this point. So our F3 is what? 0. Now, how do you not get the displacement? U1, U2, U3. Remember that the question said that what determine the displacement at the node. Which is the node? What is the node? The node is what? U2, which is at what? Point O. Because the question said that the nodal displacement at point O. So the node here is U2. So U1 here. Now, since this point is static, like it's fixed, nothing is changing there. Therefore, there will not be displacement here. So the U1 also here will be what? 0. If I stretch this, there's going to be like an appreciable increase. That is the length is going to increase. That means U2 will be unknown because we have not determined it, which is what we are looking for. Then, if we look at this point, if I stretch this, is there going to be any extension here? No. So that simply means our U3 is also what? 0. Since my U3 is also 0, what I can do is what? All these parameters, just substitute here and what? Solve it using my matrices concept. So, we have 0, our F, 0, then we have, now, if I had this and this together, I'll be getting 8.6 Abi times 10 to the power 5. You can do it. If you had this and this together, you get 8.6 times 10 to the power 5. So what I want to do now is that I want to bring out the 10 to the power 5. So I'm trying to factorize so that this thing will not be too long. So my 10 to the power 5 can be outside. So by doing that, I'll be having 10 to the power 5. So what is my K1? My K1 is 5.6. Then what is, okay, minus 5.6, 0. Then this point minus 5.6. Remember that I can use it to multiply this, which is to get this answer here. Then for the addition, minus. Will this be minus? No, this should be plus. It is K1 plus K2. You can remember that it is only this one that are alternating, which is minus. So this one will be K1 plus K2. So if you add this one and this one together, you get what? 8.6. So 8.6. Then the next one is what? Minus 3. Then this point, minus 3, 0, and 3. So my U1 is 0. I only have U2 to have a value. And my U3 also is what? 0. So I've been able to get a matrix. And from this matrix, I can determine the value of U2. So we have to solve this. How do we solve? Note that the elements here must equate to elements we get from here after you have what? Simplify it. So let us do the simplification. Now, from first row, this is the first row now. 0 equals to 10 raised to the power 5. Now to do the matrices multiplication. That is 7 shape. You multiply using 7 shape. That this multiplying this. So 5.6 times 0 will give us 0 plus or minus anyone plus open bracket minus 5.6 times this will give us minus 5.6, then u, and 0 times 0 will give us plus 0. Now we know when you resolve everything here, you still going to get minus 5.6 times 6 power 5 u2. We know that this u2 cannot be 0 because this thing will lead us to 0, but we know that u2 can never be 0 because the force is being applied there. So that means this one cannot give us the answer we need. It's not sufficient to give us the answer. So we go to the next row, which is what? F. Don't forget that our F is what? 2 times 10 to the power 5. So F equals to 10 raised to the power 5, open bracket. Now you take this and use to multiply everything here. So that will be minus 5.6 times 0 will give us what? 0. 8.6 times U2, that will be what? Plus 8.6 U2. Minus 3 times 0 will give us what? 0. So from here, we have what? Now let me substitute the value of F. 2 times 10 to the power 5 equals this one, adding everything together and multiplying with this, we have what? 8.6 times 10 to the power 5 U2. So 10 to the power 5 equals 10 to the power 5. So U2 equals what? 2 over 8.6. Now if you solve this, you'll be having 0.2326 millimeter. So approximately our U2 equals 0.233 millimeter to 3 significant figure. So this is what? The nodal displacement at point O. Let's proceed. The next question is stress induced in each material. So I'm going to do the stress induced in each material here. Then how do we go about that? Now, for element 1, the stress that will be induced in element 1, it is sigma 1 equals A1 E1 then U over L1. Then how do you get the U? That is the extension in the body. The extension in this body, there's U2 here, there is U1 here, there's U3 here. That is the extension here. That will be U2 minus U1. So this will be U2 minus U1. That's going to be the extension at this point. So if you now go ahead to determine that, you have our A1, which is 2,400 times 7 times 10 to the power 4, then times our U2, we have gotten that to 0.2326 times, minus 0, and anything minus 0 is see that thing, then over, what is our L1? Our L1 is 300. So at the end of the day, when you solve this, you'll be getting 54.2733 Newton per millimeter squared. So when you approximate this, we have 54.3 Newton per millimeter square, which is what we are approximating into 3 significant figure. So that is the stress induced in this body, the first element. Now let us determine the stress induced in the second element. For element 2, so the stress that will be introduced there will be sigma 2, which is equals to A1 E1. Now at this point now, when you extend it, the stress that will be induced here, it will be going towards this here. So we'll be saying U3 minus U2 over. Now over what? That should be over the L2. So what's our A1? Our A1 is 600 times, what is our E1? our E1 is 2 times 10 raised to the power 5, then times 0 minus U2, which is what? Minus 0.2326 over, what's our L2? 400. So at the end of the day, we're getting minus 116 point, I think that should be 0.2, right? 0.3 Newton per millimeter squared. Now, I said something the other time. This is minus. Now, stress as well. We also have a compressive stress and a tensile stress. So, because we're having minus here, it simply shows that what? This is a compressive stress. So, sigma 2 is equals to 116.3 Newton per millimeter squared, which is what? Compressive stress. You can remember this from strength of material too. So, this is what? Tensile stress. So this is the stress induced in this second element, and the stress induced in this first element is 54.3 by millimeter squared. But remember, this is what? Tensile stress, and this was compressive stress. The next we're going to do is to determine the reaction force. Please take note that the reaction force is, we say, the force of attraction are equal but opposites. So the reaction force R is equals to KU. You know where this K is coming from? That is the total force induced on the object minus individual forces. Take notes. Minus individual forces. So that simply means this also will have its own vector. You know, when you talk about force, force is a vector. It is not like a scalar object that you just give us the magnitude. But for force, you must represent it in a vector notation. So for R, we are having R1, R2, R3. Then this one will be the same Kp. You know, I told you something about Kp, that is the varroa or the global stiffness. So this will be K1 minus K1 0 minus K1 0, K1 plus K2, then minus K2 minus K2, K2. Then this will give us, the U will give us U1, U2, U3, then minus our individual forces, which is what? 0. The force we got here was F, which is 2 times 10 to the power 5 Newton. And this is 0. So I want to replace everything by their value. We have R1, R2, R3 equals 10 to the power 5. You know where I'm coming from. Then 5.6 minus 5.60 minus 5.60. Then 8.6 minus 3 minus 3, 3. This will give us 0.2326. Take note that I'm using the 4 decimal place, not the approximate answer. Minus 0, then 2 times 10 to the power 5 Newton, then 0. So how do we go about this? You're going to multiply this with this, then subtract this from it, you get your R1. For R2, that's how we go about it. So let's go. We have R1 to be equals to 10 raised to the power 5, open brackets, 5.6 times 0 will give us 0, minus 5 times this will give us minus 5.6 times 2.2326 will give us minus 1.3026. Then this multiply this, then 0 times this will still give us 0 minus 0. So at the end of the day, we're going to see that our R1 is the same thing as minus 1.3026 times 10 to the power 5. Now, what is this telling us? Minus, it simply means that what? The force, the reaction force on the node 1 is what? Compressive. Because of what? Minus. So we can now say R1 approximately is 1.330, so times 10 to the power 5. So three significant figure, and we can now tell them that this is compressive force, or we can just say compression. Anyone you say is correct. So since that's what R1 is, what? Compressive. Now the next one is R2. So our R2 is equals to, now let's go. The same principle applied there, we also are going to apply it here. So 10 to the power 5, open brackets, minus 5.6 times 0 will give us 0. 8.6 times this, so 8.6 6 times 0.2326, it's going to give us 2. This is going to give us 2 here. Actually, it's going to give me 2.0004. I like to put it in approximate answer. Minus 2 times 10 to the power 5. Now, at the end of the day, you can see that this is giving me what? 3 to the power 5, 3 to the power 5. So this is going to give me R2 equals what? 0, which is correct. Because at that point, there's going to be a force of reaction. You're already having action there. And we say, when you do the summation of forces at a node, the action and reaction are equal but opposites. So when you sum them together, they become what? 0. So if you don't get 0 at the point of action of your force, it simply means what? You are having issue with a particular calculation. Because this 0.004 is not significant. So I'll just approximate and to give you what? 0. So the reactive force here is what? 0. You don't need to put Newton. So the last one, which is R3 will our R3, let me write it here. R3 equals to 0 times this will give me 0, minus 3 times this will give me 10 to the power 5, minus 3 times 0.23. So let me get that. That is minus 0.6978. Then the last one, which is 3 times 0, 0, minus 0. So at the end of the day, you see I'm getting minus. Now when I multiply this, will be giving me 6.978 times 10 to the power 4. Because this decimal point will come to this point and this will reduce. So at the end of the day, we see that my R approximately, which is R3, is 6.98 times 10 to the power 4 Newton. This is also what? It's also compression. Please take note of that. This is also what? Compression. So we are able to get our R1 to be equals to 1.30 times 10 to the power 5 Newton compression. Then R2, where the force is acting, which is 0. Then our R3, which is what? 6.98 times 10 to the power 4 Newton, which is also what? Compression. So it is only at this point that we have our force to be tensile. That is where the direction of the force. So thank you. So today we are able to solve this example 1, and we continue with the example 2 in next section. Thank you.